We present Anytime Continual Learning for Open Vocabulary Classification to appear at ECCV2024 as an oral presentation. Imagine an image classification app that correctly identifies a T-Rex but generically labels an indigo bounding bird image as bluebird. Users can provide more specific answers to improve the app's accuracy. After learning indigo bounding, the app instantly recognizes images of that category while retaining its ability to identify other objects like T-Rex, demonstrating no forgetting. To summarize, we'd like to have an anytime continual learning system that can improve models' performance efficiently anytime new examples are received and maintain open vocabulary capabilities at any time. This requires the approach to be efficient in training, flexible in inference, and can continually improve without forgetting. A previous approach has created due systems to fulfill these goals. To maintain the open vocabulary classification ability, they used a frozen clip image encoder. They built additional example models for continuous improvements on learned tasks. The clip image encoder and the example model are combined together through a weighting operation to dynamically select the better model for prediction during inference. While effective, the example model has O-log-N update complexity and relies solely on clip's confidence for weighting. We aim for O1 complexity and a more balanced weighting method. Let's explore our solution to these challenges. Our method is inspired from the dual system design, containing an original model and a tuned model. The original model contains an encoder, an original decoder, and a label encoder that converts image embeddings to probabilities for candidate labels. Our tuned model has a tuned decoder to incorporate new data. We use a novel weighting method that balances outputs from both decoders, considering the confidence of both models for more accurate predictions. Our weighting method uses both models' relative confidence for each label, calculated via exponential moving average of accuracy before updates. The confidence is updated online, ensuring optimal performance at any testing point. As we adopt a data replay, for faster training, we can store the intermediate representations by the encoder to expedite training during sampling old data. To further improve the storage efficiency when data scales increase, we developed a compression method based on PCA and weighting different patch tokens according to the CLS token. This method reduces storage by about 30 times while showing less than 1% performance difference. For efficient online learning, we form batches with each new sample plus class balanced stored exemplars. This avoids rigid and expensive batch training while allowing us to update our model efficiently with each new piece of information. We evaluate our method using the same framework as Drew's previous work. We train the model under class, data, and task incremental learning scenarios, averaging performance over all target tasks at each stage. We also test flexible inference by combining labels from target and zero-shot tasks. These plots show our method significantly outperforms previous methods in both class and data incremental learning scenarios across various stages. The same conclusion applies to task incremental learning even when being tested more frequently. The improvements on flexible inference are even more pronounced. This verifies that our method does not forget, as well as shows great flexible inference ability. Our method is not restricted to only tuning the clip decoder. After shifting the tuned model to DynaV2, the performance is improved substantially, particularly in later stages. Our compression methods has several benefits. Besides the mentioned high compression rate and minimal performance drop, compressed data offers better privacy compared to full images, which could be particularly valuable in federative learning and decentralized environments. Thank you for listening. If you're interested, please scan the QR code to learn more.